we've got a mathematical model. I want you to write this down. For number 10, it says we have to write a mathematical model relating height to initial energy. So our mathematical model starts off with y equals mx plus b. Our slope here is 2.45. And our y-intercept is the negative 0.3, means I have to move this decimal over 3 decimal places, 0.004. I don't want to do the mathematical model for it, but do you think we should drop that number? 0.004, it's really small. So let's go ahead and drop the y-intercept. I want you to write the mathematical model, do it as best you can. Remember, I don't want to see any y's or x's in it. And I also want you to figure out what the units would be for the slope. And the slope is rise over run. So I want you to think about what is the unit for rise, what is the unit for run. So take a minute to do that. For my mathematical model, I always have to include what my y variable is. So what would that be? Elastic potential energy. You have to look at the y-axis, see what variable that represents. Let me just move my camera. And it represents elastic potential energy. So I have EPE. You don't need to put the units for the variables. I do need to put the units for the slope, though. What is my unit for slope here? Anyone able to figure that out using the units up, rise, and run? The rise is energy, right? Energy is in joules. But joules is also the same as?
It's just newtons.
Let's go ahead and do the calculation. Newton meters per meter. I think you were looking about a spring constant. And so it ends up just being newtons. That's a hint. What's my x variable? Height. Or change in height. And then we drop the y-intercept. So we're going to say the y-intercept is 0 joules. So I'm going to simplify this out. Instead of elastic potential energy, my elastic potential energy moved upward. So it really is a conversion between elastic potential energy to gravitational potential energy. Based on conservation of momentum, they should be equal from start to finish. Now, of course, we're going to have some source of error, so we might not be perfectly accurate. But if we think about our equation for gravitational potential energy, I want you to pull out your sheet with your equations. What does this 2.45 newtons, meaning it should be a force, what does this represent? mgh. So if my equation is mgh, mass times gravity times height, and I have an equation, Gp equals 2.45 newtons times height, what would my 2.45 newtons represent? Theoretically, it's the weight. Weight is represented by force, and weight is equal to mass times gravity. So, let's actually check our data. For those of you with a calculator, I want you to multiply that value by 9.8. 256.5 grams. If I'm going to convert this to kilograms, what do I need to do? 0.001 or divide by 1,000 or move it over 3 decimal places. So I get 0.2565 kilograms. Now for those of you with a calculator, calculate this value for me. 2.5. Check it out. Our slope and the actual weight Pretty close, right? You already got this equation, but I want you to know where they come from. This is how scientists get these values from doing the experiments you did in class. Here in this data, the velocity we collected, if you notice, it makes more like this curve shape. And we've seen this curve shape before. Do you remember when we collected acceleration data in our second unit, and our acceleration was position squared? Acceleration was proportional to x squared. When you have a curve like that, you have a squared proportion. So what our proportion here is, instead of elastic potential energy, what does this elastic potential energy convert to? Kinetic, thank you. So my kinetic energy is proportional to velocity squared. It is a squared proportion, so velocity doubles, the energy quadruples, right? If it triples, you get 9 times more. We are going to graph the velocity squared converted to is equal to 0.111. I'm going to leave the units out because the units are complicated. I'm just going to say it's joules per meters per meter squared per second squared. And then my velocity times my velocity squared. So if we look at our kinetic energy equation, what should this 0.111 represent? Remember, our mass times gravity represented our 2.1. For our kinetic energy, what does the 0.111 represent? I want someone besides Alec. Avery, thank you. The mass. It's not just the mass, but it's actually half of the mass. This whole thing is this. So let's check it. If this value is equal to 1/2 the mass, what is 1/2 of the mass? Who can calculate half of 0.2545 for me? 0.2545 divided by 2.
0.127.
0.127. Good. 0.127 kilograms. Does this look like this? Pretty close. Emphasizes that our kinetic energy is 1/2 mass times velocity squared. So the point of doing this is to show you how these scientists actually came up with these equations. This is what you're going to do for homework tonight. You're going to use our elastic, gravitational, and kinetic energy equations. We call these mechanical energy because you have a quantitative value that can be calculated for each of those energy types. And that's what you're going to be doing, is calculating those energy values. This is a value for spring force, but your focus for homework tonight is just calculating energy. And the hardest part about the homework, 5-4B, is converting. So be careful when you do your problems that you convert your grams to kilograms and your centimeters to meters.